Good afternoon everyone, welcome to today's worked exam answer video. I'm having a look today at a reactions of metal ions in aqueous solution question from the AQA course. And in this particular question we're focusing on the reactions of the complex aluminium ion involving 6 water ligands, and we're going to see how that can then react with different things, have to give equations for those reactions and observations. So for part A, we've got anhydrous aluminium chloride reacting with water, and that is how we are going to generate our hex aqua aluminium complex ion, which is part of solution Y, and then specifically it says that it contains a complex aluminium ion Z and chloride ions. So got to write an equation for this first and foremost, so that's where we'll start. So aluminium chloride, ionic, aluminium +3, chloride as an ion -1, so that's going to have the formula AlCl3 plus water, and as I've said, we're going to make the hex aqua aluminium ion, and for that hexa is the prefix of 6, and then the water ligands are neutral, so the charge on the complex ion overall is the same as the charge on the aluminium ion, and then we're going to have chloride ions. So because we've got 3 chloride ions in the initial aluminium chloride, we're going to have 3 Cl- there, and then I'm obviously going to need to balance the water with the 6 there. So all of this is what they're calling solution Y, and then this is what they're referring to as the complex aluminium ion Z. Okay, that is what we need to have happen before we can then think about reactions of this with one of the bases. And the bases that you may have to do this with are hydroxide ions from something like sodium hydroxide or potassium hydroxide, ammonia, or carbonate ions from something like sodium carbonate or potassium carbonate. And I believe we're doing it with hydroxide and carbonate in this question, and there are reasons why they've chosen those two specifically, which I'll come to in a minute. They're also asking us a question next about this aluminium complex ion and how it can act as a Bronsted-Lowry acid. Now, even though the other examples in this topic are all transition metals, aluminium is also included. It's not a transition metal. None of its complex ions or the precipitates formed from those are coloured. They're either white precipitates or colourless solutions. But it's included for a number of reasons in my opinion. One, it's a bit different from all of the others in how it can react with the hydroxide ions. It's also a bit different from all of the others because we can have this acting as both an acid and a base, so it's amphoteric, which is unique to aluminium. So we do need to clearly understand what is meant by a Bronsted-Lowry acid in order to do part B, give an equation to show how the aluminium complex ion Z can act as a Bronsted-Lowry acid with water. So an acid, a Bronsted-Lowry acid, is a proton donor. So we're therefore going to be donating protons to the water. So we start with complex ion Z. So AlH2O6, 3+. Add water. So if it is this complex ion Z that is acting as a Bronsted-Lowry acid, this needs to give up protons. Now, the protons will come from separate water ligands, and each proton will be gained by a water molecule here. Now, how many protons or H's these water ligands are going to lose is dependent upon the overall charge on the complex, because when we think about these sorts of reactions from this topic, we will be forming precipitates, and those precipitates will form when there is no longer a charge on the species. Now, if a water ligand gives up a proton, it's going to become an OH minus ligand, which is then going to knock the charge down from +3 in this example to +2. And so we're going to need to do that a further twice in order to bring this charge down to 0. So 3 separate water ligands are each going to give up a proton to 3 separate water molecules. And that is going to give us, I don't know why I've done square brackets, it doesn't matter, but you wouldn't need the square brackets because there is going to be no charge on what is formed here. So we're still going to have 3 water molecules intact, but 3 of them will have given up a proton each to become OH minus ligands, and because we have 3 of the OH minus ligands and the overall charge was 3+, which came from the aluminium having a charge of 3+, there's now no charge on that, hence we don't need the square brackets. It's just a bit of a habit for me to put them in. And then the H2Os are going to each gain one of those protons, so we're going to need 3 waters to each gain a proton to become 3H3O plus molecules. The other thing we could do here is show this kind of just giving up the protons and forming this and 3 H pluses, because of course that's going to show that we've got a proton donor, but I would argue that this is equally fine, but I will include both. So if this is an aqueous solution, then that is going to be able to act as our Bronsted-Lowry acid. And all I've done is removed the water molecules, and then that would present the H pluses just as 3 H pluses on that side. Now, in theory, we could have done that like once, because every single time a water ligand gives up a proton, it's acting as an acid. I've done it to show that it would happen that many times in total to give us this precipitate. But if you did it once, you would have H2O 5, OH, just one of them, so just OH, and then the charge on the outside would be 2+, plus 1 H+. I've just chosen to do it all the way until it precipitates. So I'd argue either of those are fine for part B, but the idea is Bronsted-Lowry acid is a proton donor. Okay. Now we're going back to solution Y, and this is where having Y, Z and all these other things is a little bit confusing and frustrating, but solution Y was all of these things together. So the key thing is, again, we need to be thinking about this aluminium hexa-aqua ion complex, and we're having to describe 2 observations we would make when an excess of sodium carbonate solution is added to Y. We have to give an equation for the reaction, and in our equation include the formula of each complex aluminium species. So we're going to have the initial complex ion Z, and then we're going to make a new complex species, which we also need to include the formula of. 3 marks, 2 observations, 1 equation. Okay, so in terms of the sodium carbonate solution, it's the carbonate ions that we're interested in. They are going to react with the aluminium hexa-aqua ion. Protons will be given off by the water ligands. The difference with the carbonate example compared to the hydroxide and the ammonia example is that the carbonate ions don't just gain the proton to become HCO3 minus ions. H pluses are going to react with carbonate ions, So we're then going to have those two things reacting to give us two additional products of water and CO2. And that's where the second observation is going to come from. One is going to be for the formation of the white precipitate, the aluminium complex species. The other observation is going to come from the formation of the CO2, so we're going to get effervescence. Now, it's the same idea as what I just described, and therefore I wouldn't personally be recommending that this is an equation you learn. If you know that the aluminium hexa aqua complex ion is reacting with sodium carbonate, what I guess I would hope you would be happy to do in an exam, and of course you can just rote learn it if that's how you would prefer to go about things, but if we know how the carbonate ions are working in the sense of they're acting as a base essentially, whilst the aluminium species is acting as an acid, we're going to get the exact same complex aluminium species that we did in the reaction above, because again 3 water ligands are going to each lose a proton, so that we end up with 3 OH minus ligands, and that becomes neutral, so it precipitates out of the solution and no further reaction can take place. And then the protons that come off of there, rather than like here the water just gained those 3 protons, the protons will react with these carbonate ions, so that will then give us H2O and CO2. And the CO2 is where our second observation comes from, which is our effervescence. Now, I would not particularly want you to learn that off by heart. Obviously you can. Understanding where it comes from will certainly help with remembering it, of course. But what I might suggest that you remember is the balancing for this one, because it is a little bit frustrating in terms of the balancing, because when protons react with CO3 2 minus ions, we need 2 protons for every 1 carbonate. So it'd be 2H plus CO3 2 minus makes H2O and CO2. So if we've got 3 protons coming off of here, we'd need 1.5 carbonates, and then we'd be making 1.5 water and 1.5 CO2. That's not ideal. So instead, what we do is we double up on the initial aluminium complex ion, which means we're going to double up on the white precipitate formed, and then we, instead of having like a 2 protons 1 carbonate, and therefore having 3 protons 1.5 carbonate 1.5 water and 1.5 CO2, we're now going to give up a total of 6 protons, so we can have 3 carbonates reacting with said 6H pluses to give us 3 waters, 6H pluses and 3 CO2s. So although I've just been able to sort of explain where that's come from, I'm not going to lie, would just remember 2, 3, 2, 3, 3. Just an idea. So observations, because this is neutral, it will be a precipitate. Because it's aluminium and it's not a transition metal and it doesn't have any d electrons that can be promoted, it will have to be white. Anything that doesn't have d electrons or has a full 3d sublevel or full 4d sublevel, etc., will not have colour, so it has to be white. And then the other observation, effervescence. Okay, and then finally we're adding potassium hydroxide to solution Y, and we're doing it until it is in excess. So in terms of the reason why aluminium's included is it behaves like this with carbonate ions, just like the iron 3+ ions do. But the only one of the 4 examples for this topic that will react with an excess of the hydroxide ions is the aluminium species. So that is one of the reasons why I think it's included. The key thing is here we've got until in excess. Now, if we add hydroxide ions to the hexa aqua aluminium complex ion, we get 1 observation, But then if we continue to add hydroxide ions, something else happens. And again, the reason why it will do that is its amphoteric nature. It can act as both an acid and a base, and therefore it can either react with bases or acids. So 2 observations again needed here. For each observation, give an equation for the reaction that occurs, and again in the equations we have to include the formula of each complex aluminium species, and these 2 parts are very representative of the sort of thing you'll have to do for this topic. Lots of, can you write the equation for this, what's the observations, there's a couple of other bits, but I guess in the main this is what you need to be able to do. So let's start with the hydroxide ions not in excess. So again, it says we're adding it to solution Y, but the bit of solution Y that's going to be reacting is these hexa-aqua aluminium ions. That is a bit of a mouthful. Now the hydroxide ions from the potassium hydroxide are going to act as a base. We've heard that before, haven't we, in this video? But each OH minus is going to take or accept a proton from one of the aluminium water ligands, which is going to give it off because it's acting as an acid. And as we saw here, we're going to need 3 hydroxide ions because each hydroxide ion will take a proton from 3 of the 6 water ligands, so that we again arrive at the exact same aluminium species, Al, H2O, 3, because 3 of them have lost a proton to become OH minuses. Oops, just realised I missed my 3 out up there, my apologies. 3, that's neutral, and then if the 3 OH minuses are gaining a proton each, we're going to make 3 waters. So this is acting as a base. I know this one looks like ligand substitution, but it's not. And I guess if we think about this version, that can't be ligand substitution. If we were to replace these with ammonia molecules, we'd get the exact same aluminium-based product. The ammonias would gain the protons to become NH4 pluses. Again, that clearly can't be ligand substitution, but neither is this. This is the OH minus ions acting as bases. Observations we would make here, same as above, that is still a white precipitate. But then if we continue to add the potassium hydroxide in excess, this aluminium species will react further. So that's what we need to then show in our second equation. And because it said for each observation given equation, we've had to split these 2 reactions up. If it said straight away we were adding it in excess, we'd be going from here with the excess to this final product. So it's important we read the question carefully with this reaction involving aluminium. So we're going to then add more OH minus. And in theory, we could add another 3, and they are quite flexible here in terms of what they will let you do. You can add an extra 1 and show what happens. You could add an extra 2 and show what happens. You could add another 3 and show what happens. I've always done it where I just show an additional 1, but again, I can show you what it would look like if you did something slightly different to me. And all that is going to do is the exact same thing it's just done, only now we are going to have a charge on our complex again, because if another water ligand gives up a proton, there's only going to be 2 water ligands left. There's going to be 4 of them that are now OH minuses, and if aluminium is +3 and this totals -4, the charge on the complex is not, well, it's going to have a charge now, it's going to be negative, minus. That's going to give us a water ligand, a water molecule being made, because the OH minus is taking that proton. And because this is now charged again, it's not going to be solid, it's going to be a solution. And because it's aluminium, can't be coloured, it's going to be a colourless solution, which is our second observation. The alternative to that, perhaps there are, I guess, two more alternatives, but the common one that you may be familiar with is making all of the waters into OH minuses. So having a further 3 OH minus ions being added, each of those taking a proton from the remaining 3 water ligands, so that we have 6 OH minus ligands in that complex ion now, which means overall charge -6 plus 3 is going to be -3. And then each of those OH minuses rather, has gained a proton, so 3H2O. That would still be a colourless solution. That would be accepted. The one I did above would be accepted. So that's an either or, a bit like up here, either or, here, either or. So it just depends on what you've learned. So yeah, I wouldn't be rote learning any of the equations that I've written down there. Personally, I'd be understanding what's going on in each, what we mean by Bronsted-Lowry acid, what we mean by these acting as a base. The bit I would be remembering is the balancing in the peach colour, and you are going to need to remember the colours, which I think for aluminium is particularly easy because there's no colour, so white or colourless. For the copper ones, some version of blue, iron 2, some version of green, and iron 3, some version of brown. But yeah, hopefully that shows you how you can actually piece together these equations and not just rote learn them. But if anyone has any queries, as always, please do not hesitate to let me know. Thank you so much for watching, guys, and I hope you're all keeping well. Bye!